Hello, welcome to my channel. In today's videos, we will introduce a new topic to you about curvilinear motion. Okay, so what is curvilinear motion? Basically, is that the name state is the motion that travel in the curvilinear path, or a circular path, or the path that has a certain center of rotation or center of the curve. Okay, so to be more visual, okay, I'll introduce you to the example here on your top left corner. So say if we have a reference frame of x and y here, if for example we would given point A in this frame, and then we assign the location of point A by making the line from origin to point A and call it vector R. And that vector R have angle of theta that acts with the horizontal axis. Okay, and magnitude of this vector is called a small r here. Then we assign again the position that point outward, outward the center of R. We call it positive r. Okay, and the axis, sorry, and the unit vector correspond to that direction is called er. Okay, then we assign the perpendicular axis that perpendicular with the positive r. We call it positive theta, and the direction of the positive is correspond to the angle here. So imagine if you have an angle theta here starting from x to r, surely if it rotated, this would be considered a positive theta as well. Okay, and that again in the same sense we call the unit vector of point toward positive theta as e theta. Okay, then so we say that this this object A has circular motion path as indicated in the red dashed line. What if we wanted to find the displacement rate, or in another term, the velocity of this object A, and what would be the acceleration as well? Okay, firstly we start with the velocity, which you may know. Velocity is the change in distance, right? So in this case we assign the vector r. Okay, so that means if the theta changes by the small theta like d theta, clearly the vector r will be changed accordingly, and we call it r prime. And to write the equation of this, firstly we indicate that, okay, the vector r will be equal to magnitude r times the unit vector of er. Okay, this is true because er is pointed toward positive r always, and then it's a unit vector, so it doesn't have a magnitude. So we multiply it by the magnitude of the actual r here. So we call it r, a small r times vector unit vector of er. Okay, so if we want to know the change in this vector, okay, how would it change correspond to time? We would then differentiate it with respect to time. Then we got the vector r dot equal to the products of the product of the differentiate of two parameter that multiply together. So we got the front one, and then differentiate with the follower one, plus the front that is differentiate times the original of the follower vector. Okay, so it will looks something like this after differentiate. Okay, you can review this again, how the differentiation works in this example. Okay, but okay, regardless of that, we'll get the change in vector r in this expression. Okay, so now we look on to the how to determine the differentiate of er with respect to time, because, well, we cannot clearly see what will it change on this with respect to time of this er or e theta. Okay, so we use this same frame written here. Then we imagine if the rotation has, if the theta had changed by d theta, that means e prime and e prime, er prime and e theta prime will look like this in the red line. So in the same sense, if we try to determine what would be the what would be the displacement, or what would be the resultant vector of this change, we would then have to draw this green vector and this blue vector to indicate those. Okay, firstly let's look on the green one. Okay, so you see that the ER unit vector here is at the first time step. In the next time step, or in the next data increment, ER prime is indicated at red arrow here. Okay, so that means the difference in these two vector, it indicate at here DER, which is the kind of different from the origin ER with respect to the final ER, which it will be in this green arrow here. And in the same sense, in the blue arrow here, E theta originally was drawn here in black color, then it was changed into red color because it was rotated by d theta. Okay, so we got E theta prime. So that means the vector that is indicate the difference of E theta to E theta prime is shown at d E theta vector here. Okay, so you may wondering what is the meaning of this theta angle representative here and minus r here. Okay, I'll tell you. In this e theta, this theta angle, e theta axis will be parallel to the original positive theta. Okay, you can check it by try to draw it with your pencil and ruler. You will know that if it's perpendicular and if it rotates in the same d theta angle, this vector will have the parallel direction with the original one. Okay, the same goes with this as well. So minus r vector will be parallel with positive r, but in negative direction, in opposite direction. So that's why it indicates a minus. Okay, I know it's a lot to take in, but please bear with me. We'll get to understand each one together. Then once we know the vector indicate the difference between ER and ER prime, E theta and E theta prime, we will then be able to find this differentiate of ER. Okay, firstly, we looked at the magnitude of the ER here will be equal to the vector ER, this vector sine d theta. Okay, so this basically means that if it's just like the in geometry, if we have the kind of what's it called, the circular part like this, okay, and they have a theta here, an angle here. So if you were asked to determine what would be this kind of distance like this, if you look at it as a triangle, you will see that ER is as a radius of a circle. Okay, and if we then use geometry knowledge, ER or ER prime in that sense, like this, was times the sine of this angle, that will be the distance of this DER. Okay, so that means this equation is still true even though we change ER vector into ER prime, because again it's a unit vector. Okay, so the magnitude of this is don't really matter, will be here or here, because the result, this magnitude will turn into 1. Okay, unit vector here. Okay, we substitute this one in here, then we will get that the magnitude of DER will equal to d theta. Okay, now the next question is, how is sine d theta turn into d theta here? To answer that, you have to look on the kind of the assumption we make. So d theta is something, is some small, very small angle that we try to use as a reference that the rotation did happen. Okay, so in this calculation, imagine you have a very small angle. The value of sine of that angle will be very small. If you try on your calculator right now, you will know that the sine of, let's say, 0.005 degree or 0.0005 radians will turn into zero, the same number of the angle in radians. Okay, so this is the basically approximation to make the calculation more easier without lose so much of accuracy. Okay, this is the assumption, common assumption we have always used in this kind of problem. Okay, you can review this again of how sine of the small data will turn into the data. So we turn it to data in the radius unit. Okay, now let us move on. So since, again, like I mentioned, since the derivation assume that the small angle d theta is infinitesimally small, then that means this dr here will be parallel to e theta. Okay, I know if you draw this correctly, you would know that the angle that this was making is actually around this, like half of the angle of these two. Okay, but like I mentioned, is since this angle is very small, we will ignore that and we will assume that it was parallel like this. Okay, for easier explanation. Then this vector of DER will use this relation and substitute it in, and they will get that DER here is equal to d theta times e theta. Okay, so firstly we know the magnitude of this DER, then we determine the angle or the direction by comparing with this e theta. Then we will resolve in this expression. Okay, so DER equal to equal to d theta as a magnitude times the direction of e theta. Okay, then after that we differentiate then with respect to time. Then we will get that we will get that the change in vector ER equal to the change in theta times E theta here. Okay, so now it solved one problem for us. This unknown E theta, we could use it to substitute it in. Okay, so it will look something it will help us identify ER dot here. Okay, in the similar sense, if we look on DE theta, this angle, we would know that it would be almost parallel to ER, but in a negative direction, right? So in the same assumption, we know that DE theta will be parallel to minus vector, a unit vector ER, which would then use the magnitude of dE theta. This dE theta here is came from the similar manner with this line, so you can make understanding by yourself of how this E theta came from. Then using in the same manner, we would get the differentiate of e theta with respect to time equal to minus theta dot time er. Okay. Okay. Now that we get that, the differentiate in e theta and er, we would then complete this formula. Complete this equation. So we substitute this in here, then we would get this expression. Okay. Then, since the vector r, it represents the distance relative to the center, that means the change in this vector will result in the change in displacement, which in another term, the change of displacement with respect to time is the velocity. So that means we obtain this velocity vector with the previous statement here. Okay, then this is the background of how this famous equation came from. You will use this equation very most frequently from now. I would like you to understand how it came from. Okay, I don't want you to just memorize this without any further explanation. That's why I dedicate this slide to explain this background. Okay, now you would know that that means the magnitude of the velocity in each component is indicated here. So that means the velocity in r-axis will equal to r dot times er. The magnitude will be r dot. The velocity in theta axis will equal to r theta dot times e theta, and the magnitude will be just r theta dot. Okay, this is the importance of this slide.